So in this lecture, we're going to take a look at first-order systems and some of their characteristics. Many real-world systems are actually first-order in nature. This could be, for example, thermostats, hydraulic tanks, RC circuits, and often vehicle cruise control systems. So it's pretty important to understand these first-order systems. Well, the analytical derivations of transfer functions is ideal. Sometimes the internal mechanics of the systems are unknown or inaccessible. So in such cases, we rely on system identification, estimating system behavior from output measurements, usually using a known input like a step function. So we can also often model systems very easily using these techniques we're going to discuss in today's lecture. So first of all, we have a step input. Again, we've talked about this in the last lecture. This is simply we go from 0 to some known value, uh, unit step, and then we look at how the system responds. So a first order system has a transfer function of the following form, where K and A are both constants. So K is known as the system gain, and A is the system pole, but as we'll find, that's also the time constant. Uh, so this is tau, which is, for an exponential function, the time constant is 1 over A. That's the A value that goes in here in the transfer function. So if you do an inverse Laplace transform, what you'll find in the time domain that your function looks like the following. Y sub t equals k times the quantity 1 minus e to the minus at, where a is, again, related to the time constant. The time constant, as you may remember, is the time it takes for the response to reach 63% of its final value. And this is the foundation of experimentally determining a system's parameters by measuring this time constant. So the rise time is another value that you can solve for and derive. It's the time for the waveform to go from 0.1 to 0.9 of its final value, and that's given by 2.2 times over A. Our book has these equations as well. There's also a value of what's known as the settling time. It's the time it takes for the response to reach and stay within 2% of its final value, and that's given by 4 over A. So here we can see each of those quantities represented on a typical graph of a first order system response to a step function. So here, we have 1 over A, that's the time response, the time constant. And we have T sub R is represented by about 2.2 times over A. And then we see the settling time is over here at 4A. And you can see what these values are um, based on the definition. So it's pretty easy once you plot this to determine what this A value is. So let's look at a practical example. Let's say we have the following system response to a step function here. Let's see if we can determine what the transfer function is from this data. So the first thing we need to do is identify the final state value. So here we look, and so it looks like it levels off about 0.72. We can compute 63% of that value. That's 0.45. And then we need to find what time it takes to reach the 0.45. So if we come up along here, then drop down, we can get that about 0.13 seconds. And again, this graph would be better if it was more partitioned, but let's say it's 0.13 seconds. So having found that, we can find our system pole. We can find the A value. It's 1 over tau. 1 over 0.3 is about 7.7. We can use that value to find K. So K over A is, um, so this is 0.72. So that's our, that's our steady state value. So we can find K equals 0.72 times A, which is 7.7. So K is equal to 5.54. So finally, our transfer function is K over S plus A, or 5.54 over S plus 7.7. And here we've determined our transfer function from experimental data. So the key takeaways here is that you don't always need to know the internal system details. We can apply step response to the system, and that can tell us a lot of information. First order systems are defined by just two parameters, the gain and the time constant. And it's a practical tip, always check for overshoot. If if the system doesn't, if the response output doesn't have an overshoot, uh, and the rise is exponential, you're likely dealing with a first order system.